Hi friends, welcome back to yet another video. In this particular video, I'll be talking about non-ferrous alloys. We have started talking about non-ferrous alloys. In the previous video, we have seen copper alloys and we have seen aluminum alloys. So now let's go ahead and have a look at titanium and its alloys. In this video, I will be briefly touching upon titanium and its different alloys. It won't be a very descriptive one. So we'll just touch upon the key properties of titanium and a few of its alloys and why is it so popular. So without much ado, let's get started. Titanium has an excellent combination of properties. Its density is around 4500 kilogram per meter cube. You compare it with steel. For steel, this value of density is around 7800. So titanium is much light. Moreover, the melting point of titanium is 1668 degrees centigrade. If you remember, the melting point of aluminum was around 660 degrees Celsius. We had the limitation of not using aluminum for high temperature applications, but titanium is a good candidate for high temperature applications, and we see titanium very widely used in jet engine components. This is the reason. This particular fact can be attributed as a reason for that. Moreover, elastic modulus of titanium is not too bad. It is around 107 GPa. Again, comparing to aluminum Young's modulus is just around 70 GPa. I think it's better I put all these values. For aluminum, it is just 70 GPa. Here, density of steel was around 7800 kilogram per meter cube. And melting point of aluminum, this is also for aluminum, this is Young's modulus. Aluminum, the melting point for aluminum was also around 660 degrees Celsius. So these are the few benefits of titanium, and we have a few more. The strength of the titanium alloy or titanium is not too bad. Its strength is around 1400 megapascal at room temperature. So that's too not a bad value. It is having sufficient yield strength. So since density is low for titanium, the specific strength of titanium is much higher, and that's why you see titanium is very widely used in aircraft structures, especially in space vehicles and spacecrafts. We have a lot of spacecraft brackets made of titanium in a lot of the spacecrafts which you see, in a lot of the satellites you see. One limitation, as I keep saying this, you can't have one perfect material with all good properties and without any demerits or without any disadvantages. You can't have a material like Carnot cycle, or I don't know, you can't have a perfect material. So one of the limitations with titanium is that chemical reactivity at very high temperatures. So it will react with other gases and all those things at high temperatures. So this is the reason why the refining or the processing of titanium is quite expensive. That means the whole cost of this particular alloy is very high. It's not a very cheap metal to buy and use. Moreover, talking about the advantages, titanium is very ductile and it can be easily forged as well. Moreover, it is very highly corrosion. It has capability to resist corrosion almost at all environments like marine or high temperatures. And talking about a few applications where titanium and its alloys are used. Surgical implants, you see a lot of titanium surgical implants, your ligament and all those things. You will see a lot of applications of titanium in that particular area. Then, as I mentioned above, space vehicles, it is widely used. Moreover, in jet engine components also it is very widely used, because I told you the melting point is around 1668 degrees Celsius. So in compressor disk of a jet engine, I'm not going into the details of a jet engine, I can have a separate video on that, but the disc are basically onto which the blades of your compressor are put, that is made up of titanium, at least for a few of those engines. So let's continue our discussion on non-ferrous alloys. This time I'm going to talk to you about magnesium alloys. Most of you may be first time listening or thinking of magnesium alloys as a structural alloy, but believe me, they are used as structural materials. And now let's go ahead and look into their properties. So the first one to list is its density. Density of magnesium alloy is the least among structural alloys. Its density is around 1700 kilogram per meter cube. To give a fair bit of idea, the density of steel was around 7800 kilogram per meter cube. Density of titanium was around 4500 kilogram per meter cube, and density of aluminum alloys was in the range of 2700 kilogram per meter cube. And when you have aluminum lithium alloys, they have a density of nearly 2500 kilogram per meter cube. So that clearly tells you that magnesium alloys have a very low density, and their stiffness or the Young's modulus value is around 45 GPa. So for steel it was 200 GPa, for titanium it was 107 GPa, for aluminium it was 70 GPa. So it is not that stiff compared to the other alloys. Then coming to its crystal structure, its crystal structure is hexagonal close packed crystal structure, HCP structure, as shown here in this figure. We have a separate video talking about the different types of crystal structures, and also I'm not going to dwell too much upon this particular point. They are relatively soft. Then what does that mean? So mostly we can't do a lot of machining and all those in magnesium alloys, so they are mainly fabricated by casting or by hot working at around temperatures ranging from 200 to 300 degrees Celsius. Another limitation with working with magnesium alloys is that its low melting point. Its melting point is around the range of 650 degrees Celsius, similar to that of aluminium. Aluminium has its melting point around 660 degrees centigrade. When compared to titanium, it is in the 1660 for titanium, and for steel it is around 1000. For normal steels it is around 1500 degrees Celsius. So melting point is slightly on the lower side for a magnesium alloy. Let's go ahead. A few more concerns when you work with magnesium alloy. First one, it is chemically unstable and it is susceptible to corrosion in marine environment. So if your product is going to see some kind of marine environment, then it's better you don't prefer magnesium alloy as your material. Then it has good corrosion resistance and oxidation resistance in ambient conditions. Mainly with these days we see magnesium alloys have replaced engineering plastics because of the reasons listed below. It is more stiffer. I told you Young's modulus of magnesium is around 45 GPa, which is slightly on the higher side compared to the Young's modulus values of most of the polymers or engineering plastics. Then it is more recyclable and it is less costly to produce, and it has got better heat transfer properties as well. So if you closely have a look at the handheld devices like your laptops or your cameras, they will have some amount of magnesium alloy components in it. The one reason is they have a good heat transfer capabilities also, because when your chip produces a lot of heat, you have to dissipate it Now finally I would like to bring this particular portion to an end with showing you some of the examples where magnesium is utilized. To here you can see magnesium alloys being used in the Boeing 747 in the seat components, and you can see near the engine as well magnesium alloys are used. I think I've got another picture as well, so let's go ahead and look at that. So here is the other one. So you can see again Boeing 747, your rudder pedal is made of magnesium alloy, and then your cockpit instrument panel is made of magnesium alloy. So these are a few examples where magnesium alloys are very widely or are used in aircraft industries. Moving ahead to the next class of non-ferrous alloys, we would like to talk about refractory metals. So refractory metals, as the name indicates, this kind of metals have very high melting point, so they are very much suitable for applications in which high temperatures are involved. Their melting point is in the range of 2468 degrees Celsius to 3410 degrees Celsius. So niobium melting point is in the range of 2468 degrees Celsius, while tungsten has a melting point of 3410 degrees Celsius. Tungsten is having the highest melting point among metals, which is this value around 3410 degrees Celsius. One thing, if you compare these values with the other materials like aluminum or steel or titanium, these values are very high. Moreover, the reason why these materials have a very high melting point is that they have very strong interatomic bonds, and since elasticity arises from an atomic level, Young's modulus is actually the resistance the atomic bonds offer. So I would like to explain you in this way. Let's say this is my stress strain diagram. Then let's say in this portion we have linear behavior. So what happens in this portion is that the atomic bonds get stretched, and when you load the material and atomic bonds restores or it gains its initial unstretched position once you unload it. So since the bonds are very strong, Young's modulus is also quite high for this kind of metals. So when you talk about elastic deformation, it is just putting or stretching the atomic bonds, and when you have plasticity and all those things, it is almost same as when you have sliding of atomic planes one over the other. So that's why you can't restore the plastic strain, but you can always restore the elastic strain, because elastic strain is just stretching of atomic bonds, while plastic strain is sliding of atomic planes one over the other. They have a very high strength, and they have very high hardness as well. Now talking about a few applications of refractory metals, tantalum and molybdenum is used as alloying elements in stainless steel to improve the corrosion resistance. No need to explain, because they have this very high melting point and all those things. So they are added as alloying elements in stainless steel. Then we all know in incandescent lamps we use tungsten filaments, and in tungsten inert gas welding we use this tungsten as a welding electrode as well. So these are a few applications where refractory metals are used. Thanks for watching.